Right, so it's time to start the last lecture. So could you start, Stephen?
Yes, thanks. So to this point, we've built up this decomposition method and applied it to lots of examples involving loops on Poincaré duality complexes and explored various aspects of it. So on the one hand, yesterday we inserted some extra information about Whitehead products into the method. So we sort of boosted the method a little bit and then used that to say something about the homology of various loop spaces as algebras. On the other hand, on Wednesday, we talked about inert maps, which is a kind of borrowing an idea from rational homotopy theory. So today will be along the same lines again. We'll talk about some homological implications from this decomposition method that come from borrowing some ideas in rational homology, rational homotopy theory. So we'll look at exponential growth in the rational homology of free loop spaces. And so a little bit of notation. So throughout, we'll think about simply connected spaces. And we'll use script Lx for the free loop space. So literally, this is the unbased maps from the circle into X. And there's always a fibration where you could start with the free loop space and evaluate any one of the loops at the base point of X to get a point in X, and the fiber would be the base loops on X. And the goal is to study growth in the homology of the free loop space. Think about rational coefficients. So the rational people have thought about this quite a lot. And there's a nice conjecture about what should happen. And this is due sort of initially to Gromov in a special case, and was phrased differently by Vigué-Poirrier so that it aligned better with rational homotopy theory. And it says, if X is a rationally hyperbolic space, rationally hyperbolic, let's say finite CW complex, and again, simply connected, everything's simply connected, then the rational homology of the free loop space has exponential growth. So the idea is if there's infinitely many rational homotopy groups, then the homology of the free loop space should grow very fast. This is known in some cases. It's known for a wedge of spheres. And this was due to Vigué-Poirrier herself. It's known for certain connected sums of manifolds so M and N are closed connected manifolds, and the connected sum is non-trivial. So you're not taking the connected sum with a sphere. Neither M nor N is a sphere. And this is essentially due to Lambrusch. And if X is coformal. And again, this is due to Lambrusch. Okay. Now, Felix, Halpern, and Thomas have also looked at this and tried to do a couple of things. So they tried to look at some general statements about rational growth in the rational homology of a free loop space, where maybe in a fibration they're comparing one of the terms in the fibration to another. And they also looked at more finely tuned definitions of exponential growth. But in all of this, they studied this growth using Sullivan algebras. As the rational homotopy theorists tend to do. And we'll take an approach later on, which will use this decomposition method, which is an integral method. So it's quite a different method. Before we get to that, to say things a little bit more specifically, I have to run through a list of definitions. And this will take a little bit. So, but it will set the terms. So let's let V be graded vector space. It has finite type. And let's let RK equal the sum of the dimensions of the VI's for all i's less than or equal to k. So you're looking at the accumulated growth of the generating summons within the VI's. And then we say that this graded vector space grows exponentially. If you can find constants, C1 and C2 that are finite but bigger than 1, such that for some integer m, you get C1 to the k less than C2 to the k, C1 to the k, RK is squeezed between C1 to the k and C2 to the k for all k bigger than or equal to m. Okay, so this is just trying to get a handle on what you mean by growing exponentially. And this will be fine-tuned momentarily. But a related definition is something called the log index. So the log index of V is defined by, it's a lim sup over I of the log of the dimension of VI over I. Right. And if you chase this through, if the log index is small, you're growing faster. Or just a couple remarks. One is that this log index is related to a Hilbert series. Vz is a sum from 1 to infinity of the dimension of Vi times Z to the I. And this has radius of convergence call it rho of Z. It's e to the minus log index of V. Right, so you can think of this log index as got something to do with the radius of convergence of this Hilbert series associated to the graded vector space. And V grows exponentially. If this radius of convergence is between 0 and 1, and that implies that this log index is bigger than 0. So in terms of spaces, let's set the log index. We think about the homotopy groups of a simply connected space X, and we'll look at the log index of its homotopy groups, and we think of that as referring to the rational homotopy groups. So this is the log index of all of the rational homotopy groups in dimensions bigger than or equal to 2. And so it's just keeping track of the rational information. And you can make more precise version of exponential growth So this is a definition by Felix, Halpern, and Thomas. So the graded vector space. Essentially, what you want to have happen is when you have exponential growth, potentially it could come in spurts. You grow really fast and then slow for a bit, and then really fast and slow for a bit. And what they're trying to do is give a definition that avoids this, so that the exponential growth is kind of steady throughout. So a graded vector space, V of finite type. It has controlled exponential growth. If the log index is between 0 and infinity, and for each lambda bigger than 1, there is an infinite sequence n1 less than n2, and so on, with the property that the I plus first term in the sequence is less than this fixed constant times the ith term. This holds for all I bigger than or equal to 0. And the dimension of V in the nth term looks exponential, where the alpha i's tend towards the log index. All right, so it's a mouthful of a definition, but what it's trying to say is that you have some sort of even growth rather than very jumpy growth. And Felix, Halpern, and Thomas prove the following. If you have a one-connected space, and its homology, rational coefficients, is of finite type, then the log index of the rational homology of the free loop space is less than or equal to the log index of the rational homotopy groups, and this latter is equal to the log index of the homology of the rational homology of the base loop space. A word about this, I guess. This equality is really coming from Milner-Moore on the one hand. So they say that the rational homology of loop X should look like the universal enveloping algebra of the Freedly algebra generated by the homotopy groups of X. Right? So there's the connection between the homology of loop X and the homotopy groups of X. And Felix, Halpern, and Thomas show that the log index of that universal enveloping algebra is the same as the log index of its underlying Lie algebra. So that's why you get this equality. And this inequality should come from, if you look at these two ends, the free loop space is, intuitively bigger than the base loop space. So its log index should be small. So there at least is an intuitive reason why that should be true, and they go through the argument to show that it actually makes sense. Okay. So that leads to another definition of growth. Let X be a one-connected space, again with its rational homology being of finite type. And suppose it's the log index suppose that the log index of the homology of the base loop space, rational coefficients, is bigger than 0 and less than infinity. Then the free loop space has good exponential growth. If its rational homology has controlled exponential growth, and this inequality between the log indexes is an equality. And go on to show two properties of good exponential growth. So if X is a simply connected finite type wedge of spheres, then its free loop space has good exponential growth. Okay, so I guess if you've got a wedge of spheres and you look at even the base loop space, right, then you know from the Hilton-Milner theorem that that's this infinite product of spheres of arbitrarily high dimension, and it's rationally hyperbolic. So there's exponentially many rational homotopy groups, and so that has exponential growth, and then the free loop space, of course, it's got that base loop space on one end of a fibration. So you would expect it to also have some sort of exponential growth. And what the statement is really saying is that not only do you have that exponential growth, it's very well behaved. And they proved another theorem, which is more of let's say a structural theorem. Suppose you have got a fibration where all spaces are one connected. And have rational homology of finite type. If the log index of homotopy groups of Z is less than the log index of the homotopy groups of Y, so if then, whoops. Then the base in that fibration, its free loop space has good exponential growth. If and only if the fiber does. Right, so given some sort of comparison between the base and the total space in this fibration, given by their log indexes, if you have an inequality like this, then the fiber and the total space have exponential growth that's very well behaved, simultaneous. So for example, if Z So the base in this vibration is rationally elliptic. So it has finitely many rational homotopy groups. Then its log index is 0. It only has finitely many rational homotopy groups. So the associated Hilbert series is just going to collapse, really. So if y is rationally hyperbolic, then its homotopy groups grow exponentially. So we have log index that's strictly bigger than 0. And that means we're in a position where this inequality is satisfied. So the free loop space on Y has good exponential growth, if and only if the fiber does. So this theorem of Felix, Halpern, and Thomas works really well in the case where Z is rationally elliptic and Y is rationally hyperbolic. Now I'll recall a definition. In a homotopy cofibration, suspension A to Y to Z, we label the maps. The map F is inert if the loops on H has a right homotopy inverse. So this was this generalization we talked about before of the notion of rationally inert. So the rational people would just use their version of inert, but this is a sort of generalized version of it. And we'll make a slightly stronger definition. We'll say that F is strongly inert if it is inert and when you compare the log indices of Y and Z, you get strict inequality. So the log index of the rational homotopy groups of Z is strictly less than the log index of the rational homotopy groups of Y. So for again, it's set up well to deal with the case when Z is rationally elliptic and Y is rationally hyperbolic. Now here's the theorem again of Felix, Halpern, and Thomas. And this is slightly paraphrased. They said, suppose you have a homotopy cofibration that looks like the attaching map of a cell. So you have an Sn mapping to some space Y, mapping to Z. And F is strongly inert. And now they would have used the rational version of strongly inert, but it's the same as our version. It's just that loop H has a right homotopy inverse and you have this comparison of log indices for the rational homotopy groups of Z and Y. And the conclusion is that the free loop space of Y has homology, rational homology, with good exponential growth. Right, and the proof uses the Sullivan, all the machinery of the Sullivan model, as you sort of would expect from the rational side of things. So we'll give a different proof that uses these decomposition methods and that allows things to be said more generally. So we'll give a different proof, which will be simpler, using integral decomposition methods. And will be more general. Okay, so I'll write it down and then talk a bit. So this is due to Reiji Huang and myself. Now suppose there exists a homotopy cofibration suspension A to Y to Z. Right, so we've replaced this sphere by a suspension. We're going to assume that A and Z are not rationally contractible. All right, so it doesn't degenerate rationally to some sort of trivial fibration. So they're not rationally contractible, and assuming F is strongly inert. Then the free loop space on Y has rational homology, which has good exponential growth. So in comparison to the Felix-Halpern-Thomas theorem, we replaced the sphere by a suspension, and we're drawing the same conclusion. We'll give a different argument, right? And as I say, one that uses integral decomposition methods rather than the rational Sullivan model. This is kind of surprising. You're not supposed to be able to prove rational statements using integral methods. It's not supposed to work like that. So this is surprising. So F is inert, which means by definition, loop H has a right homotopy inverse. So by what we were calling corollary C, when we look at the fiber of this map from Y into Z, its fiber will be loop Z half smash suspension A. And there's a homotopy equivalence. Loop Y is loop Z across the loops on loop Z half smash suspension A. Okay, F is strongly inert. Means that, so by definition, you have a comparison of the log indices. So the log index of pi star of Z is strictly less than the log index of pi star of Y. So by the Felix, Halpern, Thomas theorem, the free loop space on Y has good exponential growth. If and only if the fiber does. And the fiber is loop Z half smash suspension A. All right, so if we want to show that the free loop space on Y has good exponential growth in rational homology, it's equivalent to show that this space does. Right? But rationally, any suspension is homotopy equivalent to a wedge of spheres. And in our case, we've got loop Z half smash suspension A is homotopy equivalent to loop Z smash suspension A, wedge suspension A, and we can write that as the suspension. It's suspension of loop Z smash A, wedge A. So loop Z half smash suspension A is homotopy equivalent to a wedge of spheres. And now this other result of Felix, Halpern, and Thomas said that if you have a simply connected finite type wedge of spheres, then its free loop space has good exponential growth. And therefore, so does our space loop Z half smash suspension A, knowing that we had this condition that neither Z nor A was rationally contractible. So A not being rationally contractible means at least one of the spheres has to come from here, and you have to have at least one sphere here. So this has good exponential growth. And noting that A and Z are not rationally contractible, so this space is a wedge of at least two spheres. And that does it, right? We had the strongly inert condition gave this comparison on log indices, which says that the space that we want to have good exponential growth does, if and only if this space does. And then it's easy to show that that one does because it's a wedge of spheres, and we know the result there. Okay, so this was once we were able to use the machinery from our decomposition, it became easy to just invoke some earlier theorems of Felix, Halpern, and Thomas to have this argument just fall out. Whereas if you look at their proof, they got to work really hard with Sullivan models for these things, and it becomes difficult. I'll grant that we're using their earlier results that are in the background, but at least for this particular one, things have simplified quite a bit. And we can apply this to say something about some Poincaré duality complexes and the growth in the rational homology of their free loop spaces. So the theorem, again, due to Beiji, Huang, and myself. So suppose M is a simply connected n-dimensional Poincaré duality complex which looks like this case that we've been looking at repeatedly. So there's homotopy cofibrations where you attach the top cell to the n-1 skeleton, and it looks like it has a wedge of two spheres sitting inside it, and then some other space. And we were quite often calling this J, but we're going to demand this time that it's a suspension. And when we've got this other space mapping into M and collapsing out, we get a space Q, where the cohomology of Q looks like the cohomology of a product of two spheres. So again, M is one of these simply connected Poincaré duality complexes that looks like it has the cohomology of two spheres, a cohomology of a product of spheres embedded into it. Then if you look at the free loop space on this Poincaré duality complex, its rational homology has good exponential growth. So in particular, the Gromov Vigué-Poirrier conjecture holds in this case. And what's the argument? Again, it's going to be this sort of straightforward falling out from the decomposition method. So let's consider this homotopy cofibration. And label the maps, say F prime and H prime. We saw that the loops on H prime has a right homotopy inverse. Which says that F prime is inert. And we saw that there, through the use of what we're calling corollary C, there's a homotopy fibration. the fiber of the map from M to Q is loop Q half smash suspension J. We also saw that the loops on Q is homotopy equivalent to the loops on the product of its two ingredient spheres. And in particular, that says that Q has finitely many rational homotopy groups, so it's elliptic. Which implies that its log index is 0. On the other hand, if you look at loop Q half smash suspension J, then this is substitute in what we know about loop Q. It's loop SM cross loop SN minus M, and then half smash it with J. That would be SM cross loop SN minus M, smash suspension J, wedge suspension J. And this is a wedge of spheres rationally. Because it's a suspension, and this term is non-trivial. So long as J, I guess we can't have J to be trivial. So its log index for the homotopy groups is strictly bigger than 0. The wedge of spheres has exponential growth. We also saw that the loops on M, this vibration splits after looping. So loop on M is loop Q cross the loops on loop Q half smash suspension J. So it has, M has all the growth features that this space does. So in particular, its log index would be bigger than 0. And now, if we go to this vibration again, we've got the log index of M being strictly bigger than 0, the log index of Q being equal to 0. So one is strictly bigger than the other. And that implies that this attaching map F prime is not only inert, it's strongly inert. And now you can apply the previous theorem. Right, so the previous theorem said, if you have a homotopy cofibration and the attaching map for the map F is strongly inert, then the free loop space of the middle space has good exponential growth. So here's our cofibration. We know that our attaching map is strongly inert. So this space in the middle has its free loop space has good exponential growth. So by the previous theorem, the free loop space on this Poincaré duality complex, its rational homology, has good exponential growth. So this is something that's new, that the rational people hadn't known before. And we're getting it using this mixture of integral methods and concepts that are coming from rational homotopy theory. So that's, I mean, the result itself is kind of interesting, but this sort of mixture of integral and rational ideas is really intriguing, and I think that's the most interesting part of this. So I'll stop there for now.
Okay, thanks. Any question? Comment? Okay, so 10 minutes break. So the lecture will start at 1:05 p.m.
Steven, hi.
Hi, Norio.
Yeah. Let me ask you about your theorem with Huang.
Yes.
Okay, yeah. And it's very nice theorem, and I wonder if we can replace suspension space to a coed space.
Do you mean
Yes. That one. Yes. Yes.
this one? Yeah. Okay.
Yeah.
Yeah, I don't see why not. I mean, you would get the same vibration, except this is a coed space.
Right.
And then, so you would get the same kind of, you would be able to split the half smash.
Okay.
And so long as, I guess, your coed space and Z were not rationally contractible, it would all
No.
work out. Yes.
And so in that case also, we can conclude that the free loop space of Y has good exponential growth.
Yes.
Okay,
yes.
okay, that's good.
So,
Yes.
yeah.
Okay. Thank you.
Yeah, rationally, a coed space is homotopy equivalent to a wedge of spheres.
Yes.
So you get the same thing, yes.
Okay, right. Thank you.
Right, so it's 1:05 p.m. So could you start, please?
Thanks. So we've seen these decomposition methods applied in many situations and pulled out, different results on growth in the rational homology of free loop spaces, and this connection to rational homotopy theory called inertness, and all sorts of things. So I thought I'd mention to close some additional things that are known and some things that are not known. So the first, we looked at this family of Poincaré duality complexes. So these were all of the form they all satisfied these two homotopy cofibrations. You have attaching map for a top sphere, mapping to an n-1 skeleton, which looks like a wedge of two spheres in some space J. And this J, when you include it into M and collapse it out to get a space Q, Q looks like, cohomologically at least, a product of two spheres. And all the cases we considered, well, they've got this wedge of two spheres inside the the middle dimensions. So they all have these integral classes in well, the let's say in it's the middle homology dimensions for cohomology. Right. So what if you had a Poincaré duality complex given by a homotopy cofibration? So what about a Poincaré duality complex where all the homology in the middle degrees is torsion? There's no integral summons at all. So all of this that we've been talking about repeatedly is void. So you have a homotopy cofibration, attaching map for the top cell, factors through the n-1 skeleton, attach it to get M, and the reduced cohomology of that n-1 skeleton is just torsion. Okay. Well, some cases are known. One is if M is a 2n-2 connected, 4n-1 dimensional Poincaré duality complex, and I'll repeat with this 4n-2 skeleton torsion in homology. And let's just assume n is bigger than or equal to 2 so that things are simply connected. Well, we can express this by a homotopy cofibration. The attaching map for the top cell, that is to be a 4n-2 cell mapped to, it's 2n-2 connected. So the bottom cells are in dimensions 2n-1, and you could have cells in dimensions 2n, and Poincaré duality would exclude cells in any other dimensions up to the top one. So you'd have a wedge of some number of Moore spaces in that middle dimension. So they'd be 2n dimensional Moore spaces. So each of these is a Moore space, so it's a cofiber of a degree p to the I Ri map on a 2n-1 sphere. And Piotr Bebin and Ji Wu, using traditional decomposition methods, and Reiji Huang and myself using these cube lemma style decomposition methods, gave some decompositions in this case. So if each pi is odd, and you think about the odd primary homotopy theory of Moore spaces is well understood and well behaved. The two primary homotopy theory of mod 2 to the R Moore spaces is less well behaved. And if your exponent in 2 to the R is just 1, so if you're looking at mod 2 Moore spaces, then they tend to be very badly behaved. So we'll just restrict to odd dimensional or odd torsion Morse spaces so that we're in the healthier case. So if each prime is odd, then you can do an analysis on this that looks similar to the types of things we were doing before. So we can collect all but one of these Morse spaces and label that space A. It's a wedge of Morse spaces, so it'll be where the dimensions are high enough so they'll all be suspensions. We can map it into M and then collapse it out. And this V will be the analog of the space Q that we were playing with before. So its cohomology will be very condensed. It can't be the cohomology of a product of spheres anymore, because we've said that there is no integral summons in the middle cohomology of the M that we start with. So instead, we'll get the cohomology of this space V will be an exterior algebra on two generators, one in dimension 2n minus 1, one in dimension 2n, and V as a CW complex looks like you've picked a certain Morse space of a certain torsion order and attached a top cell. Right, so V is the analog of Q in the earlier case. Right. Like that earlier case, you want a nice decomposition of loop Q, or loop V in this case. So loop V will be homotopy equivalent to what? Well, if you write M as a product of primes, and you define a space S2n minus 1 P to the R is the homotopy fiber of a degree P to the R map on a sphere. Then this V has a product of these curly bracket spaces, these fibers of degree P to the R maps. And a loop on a sphere. Okay, so somehow think about this. You have this torsion in the middle, and that's reflected in this factor in the decomposition of loop V. And you've got this top cell, which is an integral class, or thought of another way, rationally, V would be what? So rationally, this space is trivial. So M would just be an S4n minus 1. Suspension A here was a subwedge of these guys. It was all of, so some subwedge of this. So it is rationally contractible, meaning that rationally M and V are the same. So V would have to be an S4n minus 1. And that's why you see the loop S4n minus 1 showing up in this decomposition of loop V. And what else do we know? The map loop H in this cofibration, you can show that it has a right homotopy inverse after looping. So you can apply our trusty corollary C. You would get a homotopy fibration that identifies the fiber of M into V as loop V half smash the attaching map for the top cell. And this splits after looping. I'm not giving any of the details, I'm just giving statements. Refining this decomposition of loop M, we have loop V appearing, and we know how it decomposes. And this space, well, we've taken, sorry, it wasn't a, which, I got the cofibration, so I was based it on this cofibration, so it shouldn't be, the suspension A should show up down here instead of the sphere. So we'll just fix this. If you look at this space, suspension A, so this was a wedge of Morse spaces, and loop V consists of this product of spaces. If you suspend any one of these curly bracket spaces, you get a wedge of Morse spaces. And if you suspend this, you get a wedge of spheres, but each of them in this half smash will be smashed with a wedge of Morse spaces. So collectively, this whole thing will just be a wedge of Morse spaces. And the torsion orders will depend on the primes that you see here. So some finite collection of primes. In particular, well, we've got this decomposition. It also says that Moore's conjecture holds here. So we already saw that rationally M had a single homotopy group because it was the same as the 4n minus 1 sphere. So it's elliptic. And this decomposition, if you look at the factors, so you get these curly bracket guys, they all have exponents. Loop on a sphere, it has an exponent at any prime p. Then you have a loop on a wedge of Morse spaces, and the torsion orders in the Morse spaces, there's only a finite number of these. And the Cohen-Moore-Neisendorfer theory would then tell you that the loop on that wedge has an exponent at every prime. And that was one of the conditions of Moore's conjecture. There's another case. If you were to look at, so that deals with 2n minus 2 connected 4n minus 1 dimensional Poincaré duality complexes. If you look at the other parity, so I'll make this a remark rather. If M is a 2n minus 1 connected 4n plus 1 dimensional Poincaré duality complex. So again, you can only have, its n minus 1 skeleton would only have cohomology in degrees 2n and 2n plus 1. So the homotopy equivalent to a wedge of spheres and more spaces. Let's exclude the sphere case because we know how to handle that. So if it's just that wedge of more spaces in the middle dimensions, what can you do? Well, unfortunately, in this case, there's no analog of this space V. Right, so there's no space with the right cohomology where instead of having an exterior algebra with a 2n minus 1 and a 2n generator, you would hope to have something that had the cohomology of exterior algebra on a 2n and 2n plus 1 dimensional generator, but no such space exists. So a different approach is needed. Okay. And this has been worked through to some extent. And it's been worked through not just for 2n minus 1 connected 4n plus 1 dimensional Poincaré duality complexes, but in the whole n minus 1 connected 2n plus 1 dimensional setting. So let's just do that. So if M is an n minus 1 connected 2n plus 1 dimensional Poincaré duality complex, whose 2n skeleton has cohomology that's just torsion, then so there's a homotopy cofibration that expresses the attaching map for the top cell. In the middle dimensions, you just have a wedge of more spaces. And we're going to assume that each of these primes is odd, as before. And we'll assume that F is an attaching map of a certain form. All right, so this won't deal with all cases, but it will deal with some of them. So assume F is of the form, it's a sum of Whitehead products and maps that pinch trivially to a fixed wedge summon of this bigger wedge. Say, well, we can arrange it so it was the first one. So we need a sort of a different approach here. And the data we'll use for theorem A would be start with this cofibration. We set things up so that if we pinch to this fixed wedge summand, then F was the sum of Whitehead products. So each of them would compose trivially down to this fixed wedge summand. And we've said that it might be some sum of other terms, but included in the hypothesis is that they all pinch trivially to this thing. So there'll be an extension across to the cofiber. And then you could take fibers and apply theorem A. And you end up with loop M being loop on this fixed Moore space across the loop of a sphere, wedge, a large wedge of Moore spaces. So without going through any of the details, I think the point is that you have a situation here where you need a slightly different approach than the one we were using for these Poincaré duality complexes in this class MN that we were looking at. And we can't resort to using our favorite corollary C, so we have to go back to the main theorem from which it came, theorem A, and look at this larger context and try and extract information out of it. And it turns out you can do so provided you have enough conditions on the attaching map. Okay, so this may not deal with all 2n minus 1 connected, or n minus 1 connected rather. Two n plus 1 dimensional Poincaré duality complexes. It is enough to cover the simply connected 5-manifold case, or Poincaré duality complex case. So on the one hand, case A would, of the 2n minus 2 connected 4n minus 1 dimensional case, they're all done. Okay, so it was really the outstanding cases were the 2n minus 1 connected 4n plus 1 dimensional ones. The first example of which would be simply connected 5-dimensional Poincaré duality complexes. But work of Barden in the manifold case and Stocker in the Poincaré duality complex case were simply connected 5-dimensional manifolds. Stocker, so they were thinking geometrically and trying to classify these guys, and Stocker wrote down explicitly what the attaching map for the top cell was in every case, and you can check that it was of the form that would fit what we just did. It's a sum of Whitehead products and maps that pinch trivially to one of the fixed Moore space wedge summands. So, but this does leave some cases unaddressed. So here's an open problem. So find decomposition for all n-1 connected 2n+1 dimensional Poincaré duality complexes, say M, whose 2n skeleton is torsion. So that's the non-torsion case we know how to do. Some of the torsion cases we know how to do, but not all of them. So the problem is try and sort that out. And you know, I give yourself a break and look at odd primary torsion, which is what we were considering all along. All right, and then I guess you could add another question. What happens if p equals 2? That would be much harder, I think, just because the homotopy theory of two-dimensional of mod 2 Moore spaces is so poorly understood. Okay. In another direction, we can look at something called two cones. So a two cone is the homotopy cofiber of a map between two suspensions. Or two co-H spaces. So, for example, let's think of, so an example we've been talking about is many of these Poincaré duality complexes. So these n-1 connected 2n dimensional Poincaré duality complexes, right? You had a 2n-1 sphere attaching to a wedge of n spheres to produce the Poincaré duality complex, and that's exactly a two cone. So we can think a general setup where we look at suspension X, wedge suspension Y, and we'll attach a certain Whitehead product. So to describe that, we'll give names to the inclusions of suspension X and suspension Y into the wedge. And let's let add K of I1 and I2 be the Whitehead product where we take the bracket of I1 and I2 and then we'll repeatedly bracket it with I1. So there's K copies of I1 here. And let's define MK define MK by the homotopy cofibration. We attach by add k. So we start with the wedge, and we will attach add k. It's coming from the suspension of a k-fold smash of x smashed with y. Co-fiber we'll call mk. Right? And let's decompose the loops on mk to see what happens. So we need, to describe it, we need an auxiliary map. So let's define a map gamma k by looking at, start with suspension x, wedge suspension y. And then we'll map in all of the adds of lower index than k. So we'll look at a wedge of add t's where t runs from 1 up to k minus 1. And then compose that into mk. Right. Oh, and I guess we want to go from the 0th one. So where add 0 of I1, I2 is just I2, the inclusion of suspension y into the wedge. So let's note that there's an extension where if you look at if you pinch to suspension x, then this Whitehead product add k composes in trivially, so you'll extend across to the co-fiber, and you can apply this. You can take fibers now and apply theorem A. And from theorem A, you end up getting a homotopy fibration that looks like take mk and map it to suspension x as here. You can identify its fiber as this map gamma k. And that splits. So the loops on mk is the loops on suspension x cross the loops on this wedge. So you have this decomposition of a certain two cone. So this mk is an example of a two cone because you've got a map between two suspensions and you've taken its co-fiber. You can find a decomposition for it. If each of the x, so if x and y are both spheres, then this becomes a wedge of spheres. So we could write loop mk is loop suspension x, so that would be loop on a sphere, cross loop on w, where w is a wedge of spheres. And in particular, if you go back to these grand problems we have of looking at problems related to the homotopy groups of a space. So there would be at least two spheres in W. So NK would be rationally hyperbolic. It would have infinitely many rational homotopy groups. It would have no exponent at any prime P. So Moore's conjecture holds. And it would also be mod P to the R hyperbolic for any prime P and any R. So its torsion homotopy groups would have exponential growth for all primes P and all primes R. And so here's another example of families of spaces that you can get a grip on using these decomposition methods. And of course, this leads to a sort of general open question, which would be, okay, so you're motivated by something like Moore's conjecture, but it's a very hard problem. So it's unlikely that in our lifetimes, anybody will completely solve Moore's conjecture, but what you might do is find families of spaces that satisfy it. So find other families of spaces satisfying Moore's conjecture and which are mod P to the R hyperbolic for all primes and R is bigger than or equal to 1. Okay. So this, in a sense, the two problems here on sort of finishing off the torsion Poincaré duality complex case and saying more about other families, perhaps other families of 2 cones or 3 cones or what have you. These all relate to these grand questions about global structure within the homotopy groups of spaces. Another thing that came out of this series of talks was this very sort of intriguing connection between rational homotopy theory and integral homotopy theory or torsion related homotopy theory. So a third sort of problem here would be to look at these rational connections a little more closely. So we saw that this rational notion of an inert map it had a useful integral analog, which let us say things about connected sums and loops on connected sums, for example. And we saw that there is, let's say, an integral approach using these decomposition methods to proving some problems, or to some proving some cases of this Gromov Vigué-Poirrier conjecture. On exponential growth in the homology of free loop spaces. This suggests more should be happening. All right, so this is a very loose statement, so I won't even call it a problem. So this is an open question, is just find more connections between, say, rational and non-rational homotopy. Right, and this sort of circles back to this problem of Morse conjecture again, which was this, grand vision of how the homotopy groups of a space ought to behave, in that, if you have finitely many rational homotopy groups in an elliptic space, it somehow should force the torsion to have an exponent at every prime p. Or if it's rationally hyperbolic, if there's infinitely many rational homotopy groups, it should force the space to have no exponent at any prime p. So there's this, deep view of how torsion homotopy groups and rational homotopy groups somehow influence one another mysteriously. And there's this sort of interesting decomposition method that we've been looking at, which somehow says, yes, there are some concrete connections between rational and non-rational homotopy theory, and it would be interesting to see if there's more. So I think I'll end there, and I'd like to thank you all very much for patiently listening to me for many hours. I've had a very good time. I hope you've had an equally good time.
Thank you very much.
Thanks again.
Okay, so any questions or comments? All right, so let's thank Professors Theriault for nice lectures. Thank you very much.
Thank you.